Hello, my name is Daniel Gitlin. Here is my term project. Sorry for sounding like this. I'm a little bit sick, but let's get into this thing. To start off, this data set is a project consisting of sensor data from a pump machine over some time. It includes 52 timestamps, 52 sensor readings, with a machine status of normal, recovery, broken. Um, This data set has about 200,000 entries, and I started off by loading it from a CSV file into a pandas data frame, and then I checked all the statistical measures of the data and found null values. I found that sensor 15 had about 22,000 null values. Sensor 50 had 77,000 and Sensor 51 had 15,000. So I decided to drop those because if a lot of those are missing, I don't see how it could really give us answers for how sensors should respond based on sensor data. Next, I assessed the skewness of each sensor's distribution. While many sensors have uniform distribution, many of them did have outliers, but and also the significant amount of missing data, I also decided to impute them by either the mean or medium on the skewness. So after dropping the certain models, I still had a bunch of null values for a bunch of sensors, so I filled them up based on the skewness of that sensor and put either the mean or the medium inside of it. And to see the distributions, I have a box plot, like a lot of outliers on each sensor. But what I realized is the first 10 sensors, the values are all pretty low, except 3. And then from 13, it scales all the way up to about 32, and then it drops back down. So, like, in batches, they're about like the same. Oh, not the conclusion. Oh, sorry about that. Let's go back here. Alright, these are the distribution of all the sensors. Um, when you compare it to these sensors 0 to 11, about 0 to 11, they got about all a normal distribution, and then it changes, but it kind of goes into like a pattern after every bit. Dealing with outliers was a little bit complicated because I didn't want to take away too many outliers that might have indicated machine failure, because usually in this scenario, outliers could possibly mean machine failure, but there was only about 7 entries of broken data, and I think it was 14,000 or more of recovering. So instead of just removing the outliers, I decided to cap them, so so I don't lose broken machine status data. And also, while examining the data, I realized there was lots of noise. So to address this, I preferred a simple moving average on the sensor readings to smooth out the data, because the data is very clunked up together with a bunch of sensors, so it's kind of hard to see the trends. So this is the before. This is the after. All the lines a little bit smaller. You kind of see the trends a little bit better. But something you do realize when looking at this, sensors 38, 39, 40, and kind of up to 50 at the about, not exactly the timestamp, but at a certain timestamp for every single one of them, there's a big drop in sensor data that goes negative. So that kind of caught my eye and wanted to check on like what's going on there. when sensor reading is dropping down, like these, dropping all the way down. All sensors have that. Oh, this is a histogram. It's the histogram after performing SMA. And for the data analysis, the average sensor readings for broken were negative zero point 0.2, normal were around 0.05, and recovering were close to 0.72. So when I look at the broken, when I think about these averages, negative 0.2, it will be close to 0, like at the median mark, 0. And then instantly it would go to recover, dropping the values even more down. But then we'll average out on normal. So you would think of it as in this picture. The normals are averaging about the middle. Right here, recovering goes broken. Right here goes down, and recovering goes all the way down. And it happens in every single sensor that's recovering. The blue represents recovering. The red represents broken. And also, I did a correlation matrix for the sensors based on the machine status, and I found out that these sensors correlate the most to the machine status. So these are the sensors with the time series plotted, and I did the same thing for index time range between certain intervals. So for an example, I took intervals where it was recovering to have a more deep look inside of all the sensors of what happens during the recovery phase, and ended up this. So it proves that when it's normal, it averages about the same. When it goes into recovering, it averages either less or more, and broken and like about the middle. But you can see the fluctuations when it's recovering. For feature engineering, I conducted time lag analysis on the data to capture temporal patterns in the sensor readings. By incorporating time lag, it can enhance the predictive model performance. And by taking the correlation between each sensor and machine, I kept the sensors that correlate the most in the data going forward into the model, which left me with about 25 sensors. The three models I ended up using are random forest, due to high classification accuracy and ability to handle complex relationships. Logistic regression was chosen for its simplicity and efficiency, and SVM was chosen for its effectiveness in high-dimensional spaces. While I encountered a couple issues where broken status was broken status had way too little amount of data, so it was kind of hard to train the model to be trained for broken status. I tried using Smoke, but the module wasn't compatible with SKT Learn, so I decided just not to use Smoke and really predict for normal and recovering data. And also in the data, I trained it with time lagged and without time lagged, but as I did it, there wasn't any real difference between it. Didn't really help too much. Maybe I should have added more steps behind, but the precision, recall, and F1 score were also pretty good, and the accuracy though. This is for the random forest. This is for logistic regression. Random forest was a little bit better than random forest was better than logistic regression for doing recovering, but as you see in the data, it's 0 for 0 is broken, and no data for broken because there's not enough data. And SVM also, which SVM did do better than logistic regression slightly. And so I did cross validation to get a better understanding of how good these models are. I did a 5-fold and logistic regression. accuracy was at a 0.97, F1 score 0.98, random forest 98, and also for F1 score, and SVM. And since random forest and SVM were about the same, it really came down to like computing power, what's the most like optimal based on the situations, and figured that random forest would be the most optimal. Um, yeah, so that's my project. Thank you for listening.